In Chapter 6, we'll be exploring more proofs, but in this case, or in this chapter, we'll be exploring more three-dimensional planes and figures and that sort of thing. To start the chapter off, we're going to start with 6.1, relating lines to planes. A couple of kind of definitions. Usually what happens is planes will be named. So if we see this figure right here, we see the plane outlined it kind of, or drawn as a rectangle. And the plane itself is T. So T names the plane. And we also see how a line goes through the plane. Right here, the point in which the line intersects the plane is called the foot. We talked about this briefly in class, but there are different ways to establish a plane. The basic is that 3 points determine a plane. So 3 non-collinear points determine a plane. So there would be one way. The other way is to have a point and a line determine a plane, and that would be because a line is determined by 2 points. So in reality, you still do have 3 points. Another would be by 2 parallel lines. And finally, the last way to establish a plane is to have 2 intersecting lines. And these are our theorems and our first postulates for the chapter. There are 2 more postulates for this section. The first one is if a line intersects a plane not creating it, then the intersection has exactly 1 point. And you can see this with the beginning diagram. If we have a plane and if the line is intersecting but not parallel with it, you see that it can only intersect at exactly 1 point right there. The second postulate is if 2 planes intersect, their intersection is exactly a line. So let's say that we create a plane right here, that's one plane, and then we create another plane that is intersecting it. Bear with the diagram as this kind of will be going through. You'll see right here that this right here would be the intersection of the 2 planes. They kind of cut through each other. And again, because planes continuously go out in all directions, this would be going this way and this way, that it creates a line for their intersection. Let's take a look at a proof. Given ABCD lie in plane M, and ST intersects plane M at point B, and D is any point on line AC, ST is perpendicular to AB, and ST is perpendicular to BC, SB is congruent to TB. And what we're trying to prove is that ST is perpendicular to BD. Now, the hardest thing, I think, in doing these types of problems is really trying to visualize the plane 3-dimensionally when it's only drawn 2-dimensionally. This is actually a triangular pyramid going above M and below M. And this right here, ADC, is a straight line. So D is on there on a flat surface. So let's think about what we are trying to prove, that ST is perpendicular to BD. And think about the ways that we can prove perpendicularity. We can prove that the angles are congruent and supplementary, and we can also try to prove that the equidistance theorem, that by proving that two of the segments or two pairs of the segments are congruent to the endpoints, which would imply the perpendicular bisector, which would imply that it is perpendicular. So let's start with our given. We're given that ST is perpendicular to AB and ST is perpendicular to BC, and that SB is congruent to TB. And based just on those givens, we can then say that AB is a perpendicular bisector of ST, because we know that it creates two congruent segments, and we're given that that the two lines are perpendicular. Now, based on being a perpendicular bisector, look at the figure and think about the equidistance theorem and what kind of things can be created from the equidistance theorem. The worst handwriting, especially whenever it does. But now, knowing that we have perpendicular bisectors and knowing the equidistance theorem, we can also say that AS is congruent to AT, and we can also say that SC is congruent to CT, again based on the equidistance theorem of a perpendicular bisector. A point on the perpendicular bisector of a segment is equidistant from the endpoints of that segment. Then they are congruent. Now, again, keeping in mind where we're trying to get to somewhere near the line BD, and looking where the point D is located, it's actually on line segment AC. If you look at AC, you'll notice it's a part of a larger triangle kind of in the front, triangle ASC, and it's also on ATC. And you'll notice that two of the line segments are already congruent from that triangle. And you notice hopefully that they share line segment AC. So we can say that AC is congruent to itself based on the reflexive property. And then we can go ahead and say that the two triangles are congruent based on side, side, side. Now what that does is it proves that the triangles not only are congruent, but again the corresponding parts. So then what we can say is we can say that this angle right here, angle SAC, is congruent to angle TAC. And that's a part of the triangles in front, SAD and TAD. And then AD will be congruent to itself based on the reflexive property. Therefore, we can then say that the triangles themselves are congruent based on side, angle, side. Once the triangles are congruent, that allows us to say that SD is congruent to TD based on CPCTC. Now let's look back at the diagram and again think about where we are trying to go with this. If you look at now this triangle right here, line segment ST to SD, if we kind of redraw that on the left, we can see how the segments are kind of congruent and how it looks. Now, if you notice, we now have two sets of congruent segments going to an endpoint of another line segment, which means we've established a perpendicular bisector based on the equidistance theorem. And since we have a perpendicular bisector, we've now just proven that ST is a perpendicular bisector for BD.